better get the recording done because people are probably just watching that. Okay, so today we will go over sections 2.3 and 2.4. Before this coming Monday, watch the video lectures for sections 2.5, 6, and 7, and begin the discussion problems on your own. I will email discussion problems for 2.6. All right. Last time I gave you this one problem to try for next time. It's right here. Okay, so last time I assigned this problem. So let's start with that. Okay, you've got a vector v of length 5, 30 degrees inclination from the positive x-axis, and vector w, length 4, with this angle 40 degrees from the negative x-axis. Find the components of v plus w and round to 2 decimal places. Okay, well, normally when you talk about the angle of a vector, it's always in the counterclockwise direction from the positive x-axis. So since this angle is 40, this angle right here is 80 degrees. Okay, so v, or w, okay, has the following components. Its length of w cosine 80, length of w sine 80. And v, well, we've already got that angle, is length of v cosine 30, comma, length of v sine 30. So the sum, v plus w, right, where length of w is 4, so it's 4 cosine 80 plus 5 cosine 30, comma, 4 sine 80 plus 4 sine 30. And that will give us the components of v plus w. So, we need to do a little bit of number crunching here. So I will go to Wolfram Alpha. Right, and of course, on the exam, we're only going to use, just a simple number crunching calculator. No graphing calculators, of course, no software. But I'll typically give you numbers that are easier to work with, or calculations that aren't too long. But as long as we're doing homework, we might as well make usage of this kind of stuff. So 4 cosine 80 plus 5 cosine 30. 4 cosine 80 plus 5 cosine 30. Oops. All right, so 5.02. We'll round to 2 decimal places. Is that what I said? Yeah. 5.02. Oops, this one was supposed to be a 5, isn't it? Yeah. And then the y coordinate is the same as this, just with signs. 6.44, we'll say. Right, and notice the vector is in the first quadrant, and I seem to...
I have a quick question, I'm sorry.
Yeah.
Would the angle be 80 degrees? Because wouldn't that be 80 plus 40 is 120, and it's supposed to be 180?
I don't know how I got that. 140. Right.
Yeah.
Not sure where I got the 80 from. Okay. 140. Now, I noticed something was wrong there because, oops. No, 140. This is 30. Because this vector is like right there, which is obviously not correct. Right? The sum of these two vectors is no way is going to be that. The sum of these two vectors is going to be right about here, yeah? Because, you have this parallelogram kind of business going on, so clearly that's the sum in the first quadrant, but close to the y-axis. So this is 120. 120. So go back and fix that. 5.96. And with the cosine, uh, 2.33.
Wasn't it 140?
Oh my goodness, what is? $140. Yes. One more time. 140. 1.27. So that is the 1.27. That's the x coordinate. 4 cosine 140 plus 5 cosine 30. Guys, it would be easier if we just spoke rather than using the chat. Yeah, exactly. And now for the sine y coordinate, 5.07. All right, so that's, more along the lines of what we're looking for, something that's pretty close to y-axis. All right. So that's part A. Part B, or part 1, I guess. Part 2, find the length of V plus W. So, well, that's easy. So 1.27 plus 5.07 to the square root. One thing that's nice about, to the, what did I do? Oh, I don't need this parentheses here. One thing that's nice about Wolfram Alpha is that, like, when you hit enter there, it tells you, well, this is what I think you mean. So you write something up here, and the expression's kind of funny looking, but it'll tell you right here, I think you mean this, and yeah, that's correct. So 5.22 is the length. Which is close to what the y component is, right? Because it's almost parallel to the y-axis. Part 3, find the angle between v plus w and the y-axis. Do you remember how that goes, guys? The angle theta?
Arctan of y over x, right?
Yeah. Arctangent of the y over x. The sine over the cosine. 5.07 over 1.27. As long as you're in the first or second quadrant. If you're in the third or fourth quadrant, you need to rotate 180 degrees backwards to get you into the first and second quadrant, and then do the arctangent and add the 180 back at the end. So arctangent 5.07, 5.07 divided by 1.27. So that's in radians, 75.94 degrees. Right, so we redraw that picture. All right, here's V plus W right about there. All right, so 75. So this is about, well, I'm not even going to label it. So vectors in two dimensions, you can talk about them in terms of coordinates, the x-coordinate and y-coordinate, and you can talk about them in terms of lengths and angles. One way or the other, you can get the information one from the other very easily. Okay. So moving on to section 2.3, I guess I should open my book, open stacks, calculus 3. Dot product. The dot product is, and the cross product are pretty neat. A lot of nice geometric information encoded in there. Alrighty, so starting with number 125. So in number 125, you've got these vectors u and v, and you're just taking the dot product. So 2, 2, negative 1, negative 1, 2, 2. So section 2.3. 125. So it's just 2, 2, negative 1, dot product, minus 1, 2, 2. So simple enough, it's 2 times minus 1 plus 2 times 2 plus minus 1 times 2. So minus 2 plus 4 plus 2 is 0. So what does that tell you, by the way, since the dot product is 0? What does it tell us about these two three-dimensional vectors?
They're perpendicular?
Yeah, perpendicular. Or orthogonal is the fancy term. Right, so, and actually their lengths are the same as well. Okay, so 90 degrees. So remember, right, the dot product u dot v, right, it is equal to this. When you know the coordinates, you can calculate the dot product that way, but the definition of dot product of u dot v in any dimension is u dot v is equal to length u length v cosine of theta, where the theta is the angle between the two vectors. All right, so the dot product is positive when the not the reflexive angle, the angle that is between 0 and 180. Right, the angle between 0 and 180. Right, I mean you can also look at that angle too, but we don't want that one. So when the angle is less than 90, the dot product is positive. When the angle is greater than 90, the dot product is negative. And when the angle is 90 itself, the dot product is 0. All right, so it tells you exactly when the vectors are perpendicular, and that's already just one of the very cool things about it, just right off the bat. And how is that proven? That the dot product, right? I mean, here this was the dot product as it's defined, right? Why was the dot product then equal to this? Right? We went over that in the lecture. That is in disguise what? The law of
The law of cosine?
It's the law of cosines in disguise. Yeah. So I mean, there's a lot of interesting things encoded within the dot product. So I mean, we are measuring the angle between two vectors essentially using algebra or arithmetic, just simple arithmetic. No sines, no cosines. I mean, just knowing the fact that cosine of theta is 0 if and only if theta is 90. But we're not calculating any angles here. But it tells us what the angle is. All right, 129. So, in the following exercise, A, B, and C are given. Determine the vectors A dot B, C, and A dot C, B. So A is, so that's 1, 1, 0. These are in 3 dimensions, right? You have I's, J's, and K's. So A is 1, 1, 0. B is 1, 0, negative 1. C is 1, 0, negative 2. So A, right, it was I plus J, which in 3 dimensions is 1, 1, 0. B was I minus K, which in 3 dimensions is 1, 0, minus 1. And C was I minus 2K, which is 1, 0, negative 2. All right, so we're calculating A dot B times C. So this is a scalar quantity. The dot product, it takes 2 vectors in any dimension, the same dimension, but any dimension, and it makes a scalar. The result of the dot product is a scalar. The result of the cross product is another vector. But anyhow, okay, A dot B. So what's A dot B? It's 1 plus 0 plus 0. And we're multiplying that scalar times C. Right, so that's just a 1, so it's 1, 0, minus 2. And then we're also calculating A dot C B. So the scalar A dot C, so that's 1 plus 0 again. Oops. times the vector b is equal to, well, that's just a 1 again. Okay, so nothing too interesting there. Next problem, 132. So 132 for the following exercises, the two-dimensional vectors A and B are given. Find the angle between A and B. Express your answer in radians. Is theta an acute angle? So we'll express it in radians and in degrees. Typically, you should do such things in radians. Why? By the way, why don't you use why is radians the preferred measure rather than degrees? Does anybody have any idea? Degrees are what type of quantity, and radians are not that type of quantity. Does anyone know? You do know, just maybe you're not sure what I'm getting at. Degrees are a labeled quantity. When I say an angle is 30 degrees, right, it's 30 degrees, and 30, the number, has the label degrees attached to it. When I say an angle is pi over 2 or pi over 6 radians, we say radians just so we know, what we're talking about, but it is not a labeled quantity. It is just a number, right? It's a number that has geometric meaning, right? 360 degrees, right, is 2 pi radians, right? Because 360 degrees, right, if you take a radius, it 360 degrees is once around the circle. Sorry, if the radius is 1. If the radius is 1, what is the length of this arc swept out? We'll say r. If this is r, then the length, arc length, is 2 pi. Well, has length 2 pi. Right, so some fraction of 2 pi will give you some fraction of the total arc. Right, so like 3/4 of 2 pi, or we'll say, how much would this be? I'm sorry, 2 pi r. Right, so we call this angle 2 pi radians. We call this angle, if it's 135 degrees, right, that's pi over 4 times 3. 3 pi over 4. And the length of this arc here is r times 3 pi over 4. Right, so the angle corresponds to this length. Right, that's just a number without a label. We say labels just so we know what we're talking about. Right, so with an unlabeled quantity, like in radians, x sine x makes sense. Right, if x is an angle in radians, then the unlabeled quantity x times whatever sine x is makes sense. If x is a labeled quantity, right, so like sine of 30 degrees times 30 degrees, what does it give you? Sine of 30 degrees is a half times 30 degrees gives you 15 degrees, right? But pi over 6 times sine of pi over 6 gives you pi over 12, just pi over 12. There's no number, there's no label attached to that. Okay, so that's the essential difference between degrees and radians. Degrees are a labeled quantity. Why is 360 a full circle? Who knows? The Babylonians like the number 360 for some reason. I mean, it's a nice number. It's got a lot of divisors to it. It's close to the number of days of a year. Ultimately, it's not really known, I guess, exactly why. All right. So, I forgot the problem. So, the vector A is 2, 1. The vector B is negative 1, 3. All right, and we're trying to find this angle theta between them. Right, so the dot product, right, A dot B is equal to length A, length B, cosine of theta. So, cosine of theta is equal to A dot B over length A, length B. So, in this case, right, what do we have? A dot B is minus 2 plus 3. The length of A is square root of 5. The length of B is the square root of 10. So theta is arc cosine 1 over the square root of 10. Right, which in radians and in degrees we can find out. So arc cosine 10 to the negative 0.5. So arc cosine 1 over the square root of 10, so 1.25 radians. So approximately 1.25 radians, which in degrees is 71.57 degrees. All right, so so the angle is acute. Well, we knew it was acute over here because the dot product was 1, which is positive. Oh, wait a minute, that's 50. I'm sorry. Give you glasses, maybe. Let's try this again. .42, 81.87. So theta is acute. But, you know, of course, we already knew theta was acute because the dot product is 1. Right? So you could have known that right away. So it's greater than 0. So theta is acute. But, I mean, you know, you can find the angle exactly. And I'll give you a really neat example of, nice physical example of how this little formula about the angle between, you know, two vectors can come in handy. In section 2.7, we'll do that. All right. 135. For the following exercises, find the measure of the angle between the three-dimensional vectors A and B. Express your answer in radians. Okay, express the answer in radians or degrees. So 135, we've got 3, negative 1, 2, 1, negative 1, negative 2. So this is B and A. And again, we're trying to find, this is number 135. Yeah, trying to find the angle between them. It's the same thing in 3 dimensions as it is in 2. Right? So the dot product is something that goes for a pair of vectors in any dimension. The same dimension, but any dimension. So that was B. And this is A. So cosine of theta, again, is A dot B over length A, length B. So what do we have? Cosine theta is 3 plus 1 minus 4. Well, it doesn't matter what these are now. So this is 0, right? So 3 plus 1 minus 4. So theta is 90 degrees, pi over 2 radians. Okay. 142. So for the following exercises, determine whether the given vectors are orthogonal or not. So in 142, you have A equal to XX, B equal to minus YX, and clearly the dot product is going to be 0 here. So they're going to be orthogonal no matter what X and Y are. Right? They're non-zero numbers, real numbers, but whatever they are, it's going to be the case that they're orthogonal. So A is XX, where X is not equal to 0, and B is minus Y, where Y is not equal to 0, and A dot B is equal to X minus XY plus XY, which is 0, so A and B are orthogonal. So 143, so same kind of thing here. You've got 2 vectors in 3 dimensions, 3, negative 1, negative 2, and negative 2, negative 3, 1. So, sorry. So A dot B is equal to minus 6 plus 3 minus 2, which is 1. So A and B are not orthogonal. $168.
You said when it's positive, the dot product's positive, they're acute.
They're acute,
Angle
yeah.
between them?
Right,
Okay.
because the cosine is positive when theta is acute. Cosine is negative when theta is obtuse. Yep. And the physical interpretation of that is nice, which we're starting to get into now. So 168. There it is. Find the projection of U onto V. W, find the vector projection W equal to projection of V onto U. Express your answer in component form. B, find the scalar projection, that's just the length of W, of vector V onto vector U. Okay, so here we've got two vectors, -4, 7, and 3, 5. That's U and V. So we're doing this. This is the picture to keep in mind. And I'm drawing them with a acute angle, but it doesn't have to be. So if this is the vector, I'm sorry, which one are we doing again? We're doing the projection onto U of V. Yeah. So this is U. So from the tip of V, drop the perpendicular to the line that has U in it. I mean, U could be a small vector. U might be right here or something like that, for example. So anyway, there's a line that contains U. So just extend that line and drop the perpendicular from the head of V onto that line. So now this vector right here, this is the projection onto U of vector V. Right? And we have a little bit of a formula for that, right? What is that? Do we remember? Right. Well, what's the length? So I mean, you can memorize the formula; it's fine. But let's rederive it. What's the length of this red line here in terms of V and theta? Right. What is this length in terms of V and theta?
V cosine of theta.
Right, the length of V times cosine of theta. So that is the comp, right, of V onto U. It's the length of V cosine theta. Right, that's the length of V cosine theta, and the dotted line here, that's the length of V times sine theta. Right, but the dot product was equal to the length of U times the length of V times cosine theta. So the only bit there that's missing is the length of U, but I can put it in there. Like that. Oops. All right, and this is U dot V over, right, that's the dot product, length U, length V, cosine theta. Right, so that's the length of the orthogonal projection, U dot V over length of U. So again, the angle theta, we don't need to know what it is. We don't have to compute it. It's just done using this, this dot product. So that's the component of V in the direction of U. The component of V in the direction of U. So what do we got here? So U dot V, so that's minus 12 plus 35. Minus 12 plus 35 over the length of U, which is, let's 16 plus 49. So 50, 65. Right, so that's equal to 23 over the square root of 35. So that's the length of the projection. Now, the actual projection, okay,
Is that 65?
is 65. I swear I got enough sleep last night. Anyway, that's the length of that projection. Now, what is the vector of that length in that direction? Right? What is the vector of this length in that direction? Right? The projection of V, onto U of V, right? It's got this length, right? This is the length. And we want to multiply it by the unit vector direction. Right? So what is the unit vector in the direction of U? What's the vector of length 1 that points in the same direction of U? Right? It's 1 over the length of U times U. 1 over the length of U times U. Right? This is the length of that projection, and then this is the direction of that projection. This vector has length 1, and now you take the vector of length 1 and you give it this length, which is 23 over square root 65 in this answer. But a more useful formula looks like this. This is U dot V over the length of U squared. Length of U squared is great if you want to leave it like that. Times U. But the length of U squared as a dot product is just U times U. Or not U times U, U dot U. So that's the nice, nifty, neat little formula for the projection of V in the direction of U. So in this case, U dot V was 23 over U dot U, well, which is just the length of U squared, right? So the length of U squared, or, I mean, whichever one you prefer. The length of U squared or U dot U, whatever it might be. Anyway, we've already calculated it. It's 65 times U itself, which is minus 47. Which in the end is equal to minus 92 over 65, comma 161 over 65. So that's that red vector up there. Right? Now, why is that important? And from a physics perspective, this projection. Right? If U is some line of travel, some direction of travel, so you've got some object and it's moving across this line, and there's a force V that's acting on it. So the force this is the force, and this is the direction of travel. Right? When the force and the direction of travel are parallel, the work done is just force times distance. Okay, but here, right, they're not parallel. So the only part of F that's actually working to move in that direction is the projection of F onto V. This bit here that's left over, the perpendicular component of the component of F perpendicular to U, is not doing anything to move or prevent from moving along that line. Right? So now when you want to calculate work, right, it's instead of force times distance, it's force dot distance, where F is the force vector and D is the distance vector. So force times distance becomes force dot distance. And using that idea, we're going to be able to do some really neat work calculations later. work calculations that, take into account the most general setting that you could, that you would be using in Newtonian physics. What's next? 143, 168, 169, probably the same thing. So these are three-dimensional vectors. Same deal in 3 dimensions. So we have 3, 0, 2. Which vector is which? 3, 0, 2 is u. And v is 0, 4, 2. So the projection onto u of v in 3 dimensions, same picture applies. U dot v over u dot u times u. So u dot v is just 4, 0 plus 0 plus 4. Over u dot u, that's 9 plus 4 is 13, times u, 302. So, oh, wait a minute, I think I copied something down wrong. 2, 4, not 4, 2. So this is 8. And then u dot u is still 13, so that's correct now. So 8 over 13 times 302. So this is 24 over 13, 0, 16 over 13. And the component in the of v in the direction of u, well, you can use that formula up here, or just do the length. Just calculate the length of that, one or the other. So let's do the u dot v over the length of u. Right? In this case, it's equal to what? Well, it's 8 over square root of 13. Right? We already calculated the dot product. It's 8. And the length of u, well, it's u dot u is the length of u squared. So the length of u is square root 13. Or, you can calculate the length straight from there. The component of u in the direction of v is equal to, well, it's the square root of 24 over 13 squared plus 0 squared plus 16 over 13 squared. This one takes longer, obviously. I don't think I can do that without a 24 squared plus 16 squared. So 24 squared plus 16 squared square root. And that must be a Pythagorean triple. Or it's not, actually. So that's 8 square root of 13. Over, well, 13 squared is just 13 there. And then you take the square root of it, it's 13. Well, the square root of 13 over 13, of course, is going to be 8 over the square root of 13. Same thing, right? Has to be. All right, that was 169, 177, 180. Let's get some nice physics problems in here, hopefully. 177, here we are. So father is pulling his son on a sled at an angle. So this is like a, classic example of what I'm talking about here, right? You're pulling the boy on the sled, or with that rope there. And the sled, of course, is moving along the ground, but the rope is not, parallel with the ground. It's pointed upward slightly. So he's got an angle of 20 degrees with a horizontal, 20 degrees with the horizontal, applying a force of 25 pounds. So he pulls the sled in a straight path of 50 feet. How much work is done by the man pulling the sled round to the nearest integer? Well, it's just, right, so we've got 50 feet. And then at 25 degrees, or was it 25 or 20? 20 degrees, 25 pounds is your force. All right, so the work done is equal to, so this is force, this is distance, it's just force dot distance. Instead of force times distance for force and distance in the same direction, it's force dot distance, because that dot product just takes into account the just the component of F in the direction of D. It takes the component of F in the direction of D. What's the component of F in the direction of D? So the component in the direction of D of F, right, which we just calculated before, it's F dot D over the length of D times D. All right, that's force. That's distance. Yeah, that's force, that's distance. These guys cancel, and it's just F dot D. Pretty neat. Pretty neat. So here, we don't have the components. If you have the components of the vectors, it's easy enough to calculate. Here you actually have to use the original definition. So it's force times distance, length of force, length distance, times cosine of theta. So in this case, it's 25 pounds times 50 feet times cosine of 20 degrees. Times 50 times cosine 20. 25 times 50 times cosine 20. 1174.6. And what are the units? Right, force times distance. Force is in pounds. Distance is in feet. So the units, so when you're talking force times distance, the units are just what?
Pounds times feet.
Yeah, foot pounds, as they're called. That's the English unit of work, foot pounds. The metric unit is what? Does anyone know?
Newtons.
Newton.
Oh, I'm sorry. Newtons is force. Sorry.
Yeah, so it's Newton meters, or
Newton meters.
Yeah, Newton meters, which are called joules, right? So that's the English foot pounds, and then you have joules and metric. Joules will do it, not that. Joules, named after some guy. Not the guy from Pulp Fiction. 281. No, I'm sorry. I'm in the wrong section. 180. So we have vector P represents the price of certain models of bicycles sold at a bicycle shop. Vector N represents the numbers of bicycles sold for each model. So what is the dot product and what is the meaning? So P is price vector for different models of bike. $150, $225. And $375. And the number of bikes sold in this case was 10, 7, and 9. So P dot in this case is so it's 150 times 10 plus 225 times 7 plus 375 times 9. So in this case, it's $6,450. Right, so the units here is dollars, right? That's the number of each bike sold, and this is price per bike. Right, so $150 per this type of bike, $225 for the medium type of bike, and $375 per bike for the deluxe bike, selling 10 bikes, 7 bikes, 9 bikes. So this is so many dollars of what?
Revenue?
Yeah, revenue, sales, or whatever, right? Not sure exactly why that's an interesting example, but anyway, there it is. Let's see, 181. Two force vectors F1 and F2 are represented by vectors with initial points at the origin. The first force has magnitude 20. This isn't on the syllabus, but I was just looking at it. Maybe it's interesting. The first force has magnitude 20 pounds, and the terminal point of the vector is 1, 1, 0. The initial points at the origin. The second force has a magnitude of 40 pounds, and the terminal point of its vector is Q001. I'm not sure you can say what because the length of that is square root 2. Anyway, some sort of conversion. Let F be the resultant force. Find the magnitude. Well, this is just what we did earlier today. There's no work calculation here. And 182, that's something we'll do later on. So, alright, so, well, that's enough for that section. So, moving on to section 2.4. Oh, let's gotta be something else we can do with this section. So here's another problem, so question. So let U equal this, 3, negative 2, 4, say, and V be equal to 5, 5t. For what value of t are U and V orthogonal? Well, I got these two vectors here, U and V, and I'm asking when would they be orthogonal? What value of t would make this orthogonal. And, will we necessarily get an answer? And will that answer be unique? Well, how would I set up such a problem?
Wouldn't you just plug them all into the dot product? And then so it'd be 15 like minus 10 plus 4t equals 0.
Yeah, right. You want the dot product to be 0. So the orthogonal, if and only if u dot v is 0. So that would be 15 minus 10 plus 4t is 0. So we have 4t is minus 5, so t is minus 5 over 4. Right? So u and v are orthogonal, and that's the only solution for t. Right? Because we got a linear equation there. And a linear equation always has an answer, and that answer is always unique. Right? So this is the only possibility for t. Right? So minus 5 over 4. How about this? Let's say, so that's if they're going to be orthogonal. What if we wanted that the angle between them was 60 degrees? Well, what would we do here? It's similar calculation, but we don't set the dot product equal to 0. We set it equal to.
Would you set it equal to the length of u and v times cosine theta,
Exactly.
but instead of theta it'd be 60?
Yeah. So u dot v is length u, length v, cosine of 60, which is just a half. So what was this? It was 5 plus 4t is equal to, well, length of u is 9 plus 16 is 25 plus 4, square root 29. And the length of v is going to be 25, so 50 plus t squared times a half, so over 2. The whole thing there. What's the problem here? Can we solve that? We can. How would we do that? What would we do? Right, you'd have to square both sides. So you got 5 plus 4t squared is 29 halves times 50 plus t squared. So this is 16t squared plus 40t plus 25 is equal to, well, what's 29? 29 times 50. Sorry, 25 times 29. That was my phone. Times 25, 725. Plus 29 over 2t squared. I mean, I'm not actually going to solve it. So 16 minus 29 divided by 2. So 1.5 t squared plus 40t minus 700 equals 0. Right? So, whoops, 1.5, not 15. 3 halves. How many solutions do you get for t in this case?
2, right?
Right, and you would get 2 solutions for t. Right, because right here would be u, and then you could have v being 60 degrees over here, or 60 degrees down here, in the same kind of plane. So I guess we could ask Wolfram Alpha to solve that, couldn't we? Let's see. So 3 halves t squared. T squared and plus 40t minus 700. Solve. So yeah, I mean there's whatever. I mean, you know, those are the solutions right there. So t is equal to these numbers here. I'm not even gonna write them down. But you see that you get 2 solutions, right, to give you these 2 different angles here. The same angle, but sort of in 2 different directions, right? So some other cool things, you know, consequences of the dot product. All right, let's go on to section 2.4 on the cross product. Let us take 5 minutes. So it's 7:43. Let's come back at 7:47, okay? Or 7:48. Hi guys. Alright, we're back. So, cross product. Alright, 183. First one. Find the cross product and then express the answer in component form and then sketch the three things. So with 183, so section 2.4, 183. So you've got U equal to 200, V equal to 220. So the drawing of those, so U is going to be here, and V is going to be here in the XY plane, both of them, right? This is the x-axis, the y-axis. That's U, that's V. So the cross product is going to point in which direction? Right, the cross product, U cross V, is going to be perpendicular to both U and V. So which way does it point? Right, U and V are both in the XY plane. What line is perpendicular to the XY plane? Well, the Z-axis. And the cross product either points up the Z-axis or down the Z-axis. Which one is it? How do you determine? How you determine which way it goes, right? You're doing U cross V. So you you take your right hand, whether or not you're right-handed or you're a lefty. You take your right hand and you point your fingers, your four fingers, okay, in the direction from U to V, in the rotational direction from U to V. And then your thumb, okay, is pointing in the general direction of U cross V, either up the Z-axis or down the Z-axis. So in this case, right, here's the fingers of your right hand. Finger, fingers, fingers. And then your thumb is pointing up-ish. Right, so U cross V, being perpendicular to both U and V, must be on the Z-axis because they're both in the XY plane. And then you determine whether it's up the Z-axis or down the Z-axis using that right-hand rule. Okay. So then how do you calculate the cross product? U cross V, you set up that 3 by 3 determinant, I, J, K, U first, 200, V, 220. Component-wise, this is how you do the component. And the result, so in the X component, you have this 2 by 2 determinant, 0, 0, 2, 0. And in the Y component, you have this 2 by 2 determinant negated, 2, 0, 2, 0. And in the z component, you have this 2 by 2 determinant negated. 2, 0, 2, 2. Or not negated, sorry, just that 2 by 2 determinant. You only negate the one in the middle. Right, so that one's 0, right, because this is 0 minus 0, right, the forward descending diagonal and the backward descending diagonal, the difference of the two, but they're both 0. This one, the forward descending and backward descending, both 0 again. And this one is 4 minus 0. So 0, 0, 4. So that points up the z-axis as we expected. All right, and it's twice the length of u. And the physics interpretation of cross product has to do with torquing force, which we'll discuss later.
Where could you put the V in order to make it so it's on the negative perpendicular?
If you put it over here.
So there's anywhere on the other side of U there?
Yeah, if V was over here in the XY plane. So then, if you curled your fingers in the direction from U to V, right? If you were kind of standing over here, right, and you curled your fingers in the direction from U to V, you'd be giving the thumbs down symbol, all right? You'd be pointing thumbs down,
okay,
rather than thumbs up. So thumbs up, thumbs down. So if you imagine U and the V, U stays right there and V is kind of just rotating. So rotating like that. The cross product is 0 when U and V are parallel, because the length of U cross V is length U, length V, sine theta. So the length of the cross product is 0 when theta is 0 or 180 degrees. And it's negative when theta exceeds 180, it's between 180 and 360. That's when the sine is negative. It's positive when theta is between 0 and 180. All right, that's where sine is positive. It's positive in quadrants 1 and 2, negative in quadrants 3 and 4, and 0 on the x-axis. So, positive cross products when V is here, and then negative cross products when the V's are there. Or, not the length, I'm sorry. What am I saying here? Length of U, length of V. Right, when the angle is measured, when the angle is measured acutely, of course. Right, so I mean, if you had an acute angle here, then your fingers start with the U and go to the V in this direction, if you want to measure the angle acutely. But if V is over here, then the acute angle is in this direction. All right, or sorry, from U to V. The acute angle would be in that direction rather than that direction. So that reverses, and your thumb would be going down. All right. 183, 199. For the following exercises, the vectors U and V are given. Use determinant notation to find vector W orthogonal to vectors U and V. So that's the cross product, right? If you've got two vectors in 3 dimensions, right, you want a vector perpendicular to both Well, that's the cross product. And as a matter of fact, if you've got two vectors in 3 dimensions, they always exist, and so they define some plane. Right? So these two vectors live inside of some plane. Right? Then the line that is perpendicular to that plane is unique. Right? Because that line is perpendicular to you and perpendicular to V. And there's only one such line in 3 dimensions. The cross product, by the way, is only for vectors in 3 dimensions. It's a special. It does extend into 4 dimensions. It's not the same operation. It's a little bit different, a little bit more complicated. But there is a thing called the cross product in 4 dimensions, and it specializes to this 3-dimensional thing that we're looking at. If you ever get into quantum physics, they use that. Or if you're just doing just generic 4-dimensional geometry and mathematics, then you would use that perhaps. All right. I guess they would use it in relativity as well. All right, so U was equal to minus 1, 0, e to the t, and V was equal to 1, e to the minus t, 0. And you want to find a vector W orthogonal to both of them. So W equal to, and you can do U cross V or V cross U, is orthogonal to both. As is negative U cross V. The negative of U cross V is the cross product in the other direction, V cross U. So U cross V and V cross U, they're the same. They're the same up to negate. They're equal. The difference, they differ by negation. They differ by negation. And that's just because you're turning your hand upside down with the right hand rule. Right? Curling your fingers in the direction from U to V. Your thumb would go the opposite way if you want to curl in the direction from V to U. All right, so the cross product is orthogonal to both. And then, if you wanted a special length, you could calculate the unit vector in that direction and then multiply it by some special length. But here we're not doing that. So W is the cross product, U cross V. So for U cross V, you put the components of U first and then V. So this is the 3-dimensional vector. So in the X component, cross out first row, first column, and you're left with 2 by 2 determinant 0 e to the t, e to the minus t, 0. And then for the J component, cross out, first row, second column, and what's left over, you put in the 2 by 2 determinant, and you negate it in the end. And then in the Z component, you have that 2 by 2 determinant. And that's the cross product. In the book, they use the IJK notation rather than doing it this way. I really don't like the IJK too much. So anyway, this one is 0 minus e to the t times e to the minus t is just 1. So this is 0 minus 1. Here you have 1 minus e to the t. 0 minus e to the t, excuse me. So 0 minus e to the t. And in the third component, you've got minus e to the minus t minus 0. So we are left with minus 1 e to the minus positive e to the t, and then minus e to the minus t. And if you want, you can check out that those are orthogonal. Right? Let's check that u dot w equals 0 and v dot w equals 0. So it's minus 1, 0, e to the t. Dot minus 1, e to the t minus e to the minus t. So this dot product is 1 plus 0, and then minus, so e to the t times e to the minus t is 1. So there you get minus 1 is 0. And then u dot v, v dot w. So v was 1 e to the minus t, 0, dot w. So 1 times minus 1 is minus 1. E to the minus t times e to the t is 1. And then 0. So that's 0 as well. Okay, so we have this, this nice display of orthogonality with the cross product. All right, so that was 199, 203. Use the cross product to find the acute angle between vectors u and v, which are 1, 2, 0 and 1, 0, 1. So u is 1, 2, 0. V is 1, 0, 1. So first of all, let us calculate u cross v. So u cross v is equal to, I, j, k, 1, 2, 0, 1, 0, 1. So first let's calculate that. So this is equal to 2, 0, 0, 1. K is 1, 0, 1, 1. Negated. And K is 1, 2, 1, 0. So this is 2 minus 0. This is 1 minus 0. So you get minus 1. And this is 0 minus 2. Alright, so 2, negative 1, negative 2. So now the length of u cross v is equal to 4 plus 1 plus 4. So that's 9. So that's 3. So the length of u cross v is 3. Now, in the geometric interpretation of the cross product, also, u cross v, its length is the length of u, the length of v, times sine theta. So, there's u, there's v. All right, you got this parallelogram. All right, so you've got these other copies of u and v sitting around here. So the length here for this perpendicular is the length of u, and this is a theta here. So this is the opposite side of the angle. So the length right here is u sine theta. So length of u, length of v sine theta is the area of that parallelogram. Right? It's the length of the base. Right? It's the length of the base times the height. So it's base times height equals the area of this guy. The area of the parallelogram. Just base times height. And that's exactly what you're getting here. Right, so in this case, we've got in this case, we already know what the length of u cross v is because we did it component-wise. So that's 3 is the length of u. Length of u is square root 5. Length of v is square root 2 sine of theta. So 3 over square root 10 which is equal to approximately 3 divided by 10 to the 0.5. So 71.57 degrees. Okay. So with the cross product and with the dot product, you can find these angles between two vectors. Okay. And with the dot product, it can be easier. Well, of course, it only works in 3 dimensions. Well, you can do the cross product in 2 dimensions as long as you just place it in. If you have 2-dimensional vectors u and v, you can put them inside 3 dimensions by just adding a 0 component in for z. In which case, you can do the cross product that way. So it's kind of, that's nice. 211. Consider the points A, B, C. Find the area of the parallelogram with sides A, B, and AC. Find the area of the triangle A, B, C. And find the distance from point A to line BC. All right, so we have AB, AC. So this is going to be point A, which is 3, -1, 2. And this will be point B, which is 2, 1, 5. Right, it's AB, AC. And C is 1, -2, -2. All right, so AB, head minus tail, two minus 3 is -1. 1 minus -1 is 2. 5 minus 2 is 3. AC is 1 minus 3 is -2. Minus 2 minus -1 is -1. Minus 2 minus 2 minus 4. All right, so we've got A, B, A, C. And then, what were they saying here? Find the parallelogram area of the parallelogram ABAC with adjacent sides AB and AC. I mean, I'm not even telling you what D is. D is going to be the sum. D is going to be over here. Right? You got another copy of AB here, and then D will be this point up here. But we don't need to calculate it. I will draw the picture though. And so this is also the angle, the vector AB, and this is also the vector AC. And here's D. So let's calculate the cross product. So AB cross AC is YJK minus 1, 2, 3, minus 2, minus 1, minus 4. So that's going to be the 2 by 2 determinant, 2, 3, minus 1, minus 4, comma, and some more space. And then minus 1, 3, minus 2, minus 4, and then minus 1, 2, minus 2, minus 1. So this cross product is here somewhere. Oh, I did. Let me look down. There it is. So this is minus 8 plus 3. So that's minus 5. And this is going to be 4 plus 6 is 10 negated. And this is going to be 1 plus 4 is 5. So minus 5 minus 10, 5. So now the area of the parallelogram is just that length. Is just the length AB cross AC. So that is going to be 5 square root 4 plus 1 plus 1, 5 square root 6. Right, because this vector is 5 times minus 1 minus 2, 1. Right, so the length of that is 5 times whatever this length is, which is square root 6. The area of the triangle given by ABAC right, so you take that picture again, but forgetting about the D, All right, we're just interested in this triangle here. Well, the area of that triangle is just half the length of half the area of the parallelogram, right? So that's 1/2. The length AB, AC. And you can calculate, the triangle has 3 sides, right? So, I mean, you've got these 3 points, A, B, and C. And I used vectors A, B, and AC. So I used this side and this side to calculate that area. You could use any 2 sides. I could use, I could do this side and this side to calculate that area. Or this side and this side to calculate that area. So, I mean, if you've got 3 points, A, B, and C, you can calculate vectors A, B, AC, CA, CB, BA, BC, do the same calculation. It always comes out to be the same. Anyway, it's 5/2 square root of 6. And then the last part, what was it? Find the distance from point A to line BC. Wait a minute. Find the point B to the line AC, I think is what they mean. A to BC. I think they mean B to AC. I see. This is exactly what I was talking about before. There's just like typos in here. Like if you looked in the answers in the back of the book, I bet you. Let's do what I think it is. I think they mean the distance of point B to line AC, because we haven't even looked at vector BC, so I don't think that's what they're getting at. So the distance. So let's draw it so we know what we're looking at here. Right, so here, so we can forget all about that now. So the distance of point B to AC is right there. Right, so that is the length of AB times sine of theta. So that's the distance we're looking for. Right, the length of AB times sine theta. But, I would also like the length of AC in there so I could use the cross product. Right, so let's write it down here. So that distance is equal to the length of vector AB times sine of theta. But I could write it as AB AC sine theta over AC. Right, just uncanceling the AC. But now this is the length of the cross product. So this is the length AB cross AC over the length of AC. Right, and we've got all that stuff. Right, we've got the length of the cross product. It was 5 square root 6. 5 square root 6 over the length of AC. So AC, what's that length? So that is 4 plus 1 plus 16. So 4 is 20, 21, square root 21. Right, so that's the distance of point B to line AC. So the line through AC in the distance from point B is this perpendicular distance, which by trigonometry is A sine theta. A length AB sine theta. But then we can just add in the factor of AC on the top and bottom of a fraction, But this is the length of the cross product, which you already know, and then the length of AC. That's easy enough to calculate, and there it is right there. So I'm a little curious. Let's look in the back of the book. It's got to be what they mean. 211. 5 square root 6 over 59. So that is what they meant. But then you'd have to calculate a whole other cross product, so what's the point? You would have to calculate, so that's 5 square root 6 over 59. Where did it go? What number was this? So the distance of point B to the line AC. No, that. Hold on a second. What's going on? Oh, yeah. The distance from point A to line BC. So the distance of point A to line B, the line BC is right there. And so that distance is this perpendicular or something. Anyway, you'd have to calculate a whole new cross product for that. So I think this is more so what they meant. So that's not what the question asked, but this is fine. Okay, so this is the distance of B to line AC. Because it uses stuff we already know. If we were to do the other one, it would be using a quantity we don't know already. Okay, so that was 211 and 214, 221, 214. So in 214, you've got these three vectors, u, v, and w. Find the so this is scalar triple product, u dot v cross w. It is the volume of the what's called parallelepiped with adjacent edges u, v, and w. So we talked about that in the lecture. So if you've got these three vectors here in 3 dimensions, I guess I'll make this one dotted, sort of in the background. So u, v, w like that. So this parallelepiped thing, it's this sort of parallelogram box. What you need to do is copy those vectors over. So here's a copy of u. Here's another copy of u. Here's a copy of v. Oops, I messed that up. There we go. So here's a copy of v. Here's another copy of v. And another copy of v. And then another copy of u over here. And then copies of w. This one would be dashed, I guess. There's a W. So you get this thing called a parallelepiped. So it's the sort of three-dimensional analog of what a parallelogram is. So it's a box, rectangular box with, well, not rectangular, it's this box made from three parallel angles rather than like a two-dimensional polygon made from, what did I say? From three vectors, parallel copies of those vectors rather than two vectors and parallel copies of those vectors. And the volume of such a thing is the absolute value of u dot v cross w. And you can do it in whatever order you like. You can do that in whatever order you like. You can do u dot v cross w, v dot u cross w, or w dot u cross v, whatever it is. All right, and when you go through the algebra of this, what happens is it turns out to be this 3 by 3 determinant, A, B, C, D, E, F, G, H, I, where this is the vector u, this is the vector v, and this is the vector w. It's the absolute value of such a thing. Because it can turn out to be negative, depending on what order you do things in. So, in this case, it is the vectors where is it? Number 214. There it is. 3, 5, negative 1, 0, 2, negative 2, 3, 1, 1. 3, 5. V is 0, 2, 2, and W is 3, 1, 1. All right, so U dot V cross W. Now, of course, you can calculate V cross W and then take the dot product with U. You can do it that way. But this is a shortcut, and it's just this 3 by 3 determinant. And we want to do the absolute value of such a thing. So 3, 5 minus... Sorry?
For you, I think it was negative 3, 5, negative 1.
Yeah, negative 3, 5, negative 1. Right. Okay. 0, 2, and then 3, 1, 1. So that's equal to... So instead of having I, J, and K, you just have negative 3, 5, and negative 1. So it's negative 3 times the 2 by 2 determinant, 2 minus 2, 1, 1, minus 5 times the 2 by 2 determinant, 0, negative 2, 3, 1. Some space. And then minus 1 times the 2 by 2 determinant, 0, 2, 3, 1. And then you're going to do the absolute value of that thing in the end. Right? So instead of having in the cross product I, J, and K, go ahead, take it. Instead of having I, J, and K in the cross product, you get the components of U. Okay, again, you can calculate the cross product and then take the dot product with U, but this is how it works out in the end. So this is minus 3 times 4, minus 5 times 6, and then minus 1 times minus 6. Absolute value of that whole thing, which is equal to 36. All right, it's minus 12 minus 30, so it's minus 42 plus 6 is minus 36. Absolute value is 36. So that's the volume of that parallelepiped or box or parallelogram type box, whatever you want to call it. So lots of geometric meaning is encoded into these dot products and cross products. I mean, it's amazing how much. You know, it's really quite beautiful. 221. Let U, V, and W be three-dimensional vectors and C a real number. Prove the following properties of cross products. Do I need to have you guys do that? Well, that's the last problem, 235. Let's do 235 first, and we'll get back to that. Good. So here is the physics problem. Okay, so a mechanic. So torque is simply defined as cross product. So a mechanic uses a 12-inch wrench to turn a bolt. Okay, and the wrench makes a 30-degree angle with the horizontal. With a magnet, if the mechanic applies a vertical force of 10 pounds straight down. Right, so I mean, if you've ever used a wrench before, you know, you're going to pull that wrench down, typically, you know, in this kind of situation. I mean, if you I don't know how much you guys work with these things, but like, I mean, if you stuck a wrench up like that and you were sort of standing on under a car that's on a lift or something like that, you would pull straight down on that thing, right? On some sort of ratchet wrench or crescent wrench or whatnot. You'd be pulling straight down, try to loosen that bolt or whatnot. Okay, and the torquing force, the twisting force applied at P is simply defined to be the length of the cross product. Okay, so the cross product of these two vectors, the vector of length 12 and the vector of 10 pounds straight down, and the resulting force is in foot-pounds again. Well, it's not actually foot-pounds in this case. Well, 12 inches will be 1 foot, so in foot-pounds again. So torque is measured in foot-pounds. So 235. So we've got this lever L is 1 foot long, and here's your bolt. And then you've got this pulling force, 10 pounds, straight down, where this angle here is 30 degrees. Now, when you do the cross product, you have to put the vectors tail to tail. Okay, so put vectors tail to tail. So again, you've got this lever of length or magnitude 1 foot, and now you got 10 pounds going straight down. Right, this angle here was 30, and this angle here, of course, is 90. Right, so the angle theta between them is 90 plus 30 is 120 degrees. Right, so the torque applied at P, and here's P right here, the torque applied at P is the length of L, so I guess we're going to call that F. So F, the magnitude of F is 10 pounds. And the magnitude of F is 10 pounds. Going straight down. So L cross F, the magnitude is the length of L, the length of F, sine of theta. So that is 1 times 50 times sine of 120. And sine of 120 is what? Square root 3 over 2. So it's 50, or 10 pounds, I'm sorry, not 50 pounds. 10 root 3 over 2. So that's 5 root 3 foot pounds. Okay, so that's one interpretation, physics interpretation of cross product. There's also cross products involved when you're doing like angular momentums. Right, but this one is nice. This twisting force or torquing force. So the last problem, 221. They're asking you to explain why these are the case. We can look at that in the last few minutes here. U cross U is equal. Oh no, where is it? Here it is. U, V, and W are three-dimensional vectors. U cross U is 0. Why? Why would U cross U be 0? Because the length of U cross U is the length of U times the length of U times sine of theta, right? But theta is 0. Right? So the length of U cross U is 0, and the only vector of length 0 is the 0 vector. U cross V plus W is U cross V plus U cross W, or yeah, U cross V plus, well, that's just one of the rules or identities that were given. U that cross product distributes over vector addition, right? I mean, that was this section. They just give you some identities. They don't prove them. Blah, blah. Huh. Well, I gave them to you in my lecture. Yeah, here it is. All right, that's just the distributive property of cross products. Right, so 221, that's just the distributive property. Part B. So part B, this is the distributive property. You could actually like go about proving it using determinants, but I mean that's going to be like really a long push of symbols, symbolic pushing. This one is this is another one of the properties given. I don't know what you call that one. So this was another given property of cross products. And then D, U dot U cross V is 0. Why is that the case? Right? U cross V is perpendicular to both U and V. U and V, we must have that. U dot U cross V is 0, right? Because dot products of vectors, of perpendicular vectors, is always 0 if and only if. Okay. So that's it for these two sections, guys. So next time, again, I'll email you an assignment for section 2.6, but you need to watch the video lecture for 2.5, 2.6, and 2.7. Not sure if we'll get through all of that next time, but we'll give it a go. All right. Have a good evening, everybody, and we will see you next time. If you have any questions, concerns, you want to meet with me for some extra help, perhaps, just shoot me an email, okay? And we'll arrange something. All right. Have a good night, everybody.